Helen. I'm going to talk about a procedure that's been used in academia for some time, but is relatively new in the commercial space for elemental analysis of geological and metallurgical materials. It's lithium borate fusion X-ray fluorescence coupled with laser ablation ICP-MS. There are a considerable number of analytical choices available depending on the element of interest, sample type, commodity, detection limit, and if the result only need to be indicative or absolute. Current methodologies in labs for multi-element analysis can be split into a number of types. There are the partial leaches. These for most elements will not give quantitative results, but can still produce useful data. They tend to produce lowest detection limits, are lowest cost per sample, and examples are dilute acid leaches or aquaregia. Moving on to the much more aggressive multi-acid digests, including hydrofluoric and perchloric acids. These types of digest can be quantitative for many elements, but a number of minerals are resistant to attack. This digest can achieve low detection limits for many elements. A fusion digest will give a true total quantitative dissolution. It is much less prone to precipitation than multi-acid. The lithium borate fusion with XRF finish, for instance, is regarded as the gold standard for the analysis of elements present in high concentrations by a number of industries. Fusions do typically report the highest detection limits and are the most expensive procedures. Often, for a comprehensive element package, clients will request of a fusion and a multi-acid digest, which allows for a choice in terms of detection limit and true total extraction. The procedure I'm talking about here is an alternative to this approach. In wet chemistry procedures, the workflow after sample preparation is weigh, digest or fuse, with the sample ultimately being dissolved in a solution for presentation to the instruments. With this new fusion procedure, similarly the sample is weighed and fused, but not dissolved. Instead, a solid homogeneous glass disc is formed, which may either directly or after XRF analysis be presented to an ICP-MS for trace analysis. Here we have what that looks like at BV. In the foreground here you can see the platinum crucibles, which contain the sample and flux mixed. And the robot will pick up this crucible and place it in a furnace. And when the fusion is complete, pour the resultant melt into a mould to form the glass bead. The way we achieve the analysis of the solid fusion bead via MS is to use a laser to ablate the bead, generating a submicron dust, which is transferred into the MS for analysis, much as solutions are pumped and aspirated for analysis in wet chemistry. There are many different laser systems. The technology is now at a point with the availability of systems capable of sub-5 nanosecond pulse widths and short UV wavelength that they are well suited to this type of work. We use these types of lasers, namely 193 nanometers and 213 nanometer laser systems exclusively. We are about to fully automate this procedure, giving us a capacity of more than 1,000 samples per day per system. Okay, why the claim of ultimate procedure? What are the advantages when compared to wet chem, multi-acid or fusion digestion? It turns out that many of the caveats of the wet chem procedures are negated by a solid glass bead. I'll just mention a few. incomplete dissolution via acid digests. For a number of elements, elemental extraction is dependent on mineralogy. It is also dependent on digest temperature and how long the digest is carried out for. Not only can the result not be quantitative, but different labs may produce different results, as methods are not standardized. Elements often affected include the high field strength elements, such as zirconium, hafnium, tantalum, tungsten, the heavy rare earths, yttrium, thorium. Tin in cassiterite will extract less than 1% of total. I have seen samples that contain thousands of ppm tin return values of 1 to 5 ppm via multi-acid digestions. Fusion procedures do not suffer from these issues. Another issue is precipitation. Many elements may precipitate from solutions, especially if certain combinations are present in high concentrations, such as barium and sulfur will form insoluble barium sulfate. Similarly, zirconium and phosphorus will form insoluble zirconium phosphate. Examples of other elements often affected by precipitation are silver, lead, tantalum, tungsten, niobium, potassium. There's more. In contrast, these elements will not drop out of a solid bead. There are interferences caused by matrix. In MS, the main interferent is from the formation of oxides and to a lesser degree chlorides. Examples of elements affected include vanadium, arsenic, selenium, silver, cadmium, the heavy rare earths, etc. The interferents are primarily derived from water and hydrochloric acid. The interferents, these are not present in the solid bead, and hence interferences are much reduced, 20 to 50-fold. Other benefits of this approach include a relatively high sampling weight, which is critical in terms of sampling error. We are looking to increase the weight further, mainly to achieve better detection limits. The reason fusions have high detection limits in wet chem procedures is the fluxes used substantially contribute to the total dissolved solid in the digest liquor. This high salt content needs to be diluted before the sample can be presented to the instrument. The final dilution factor for fusions for MS is often 10,000 or more. The dilution of a sample in a solid bead is 10. Hence, this approach offers detection limits comparable to multi-acid digest, with the benefit of being truly quantitative, so no compromise between total extraction and detection limit. We observe great benefits in terms of washout. That is, when samples are analysed, they contaminate the instrument, and this needs to be removed before the next analysis. If not, it will affect the results of samples to follow. This effect is an order of magnitude less in laser ablation compared to wet chem. No corrosive acids are used, much better for people and equipment. Data from XRF and MS can be combined to give a massive dynamic range, no over-range reporting. All elements are derived from one digest, so it is cost-effective quantitative multi-element analysis. Elements such as chlorine and fluorine can be added, as can LOI as part of a package. So, the key takeaways are, this method simply combines the accuracy and precision of a borate fusion XRF procedure with the ultra-trace capability of ICP-MS, allowing the strengths of both methods to be combined from a single fusion digest, producing high-quality quantitative data with low detection limits in a cost-effective manner. Thank you.